Complement independent and dependent events. So this is where we ended last time. It's about how to compute for the probability of simple events. A bag contains golf balls. There are 50 of them. 20 are white, 10 are neon green, 15 are yellow, and 5 are bright orange. Let B be the event a white golf ball is drawn from the bag. Find P of B. What is P of B? P of B is equal to how many B's are there in the sample space. How often does B occur in the sample space divided by the size of the sample space? So in our sample space, we have 20 white golf balls. The size of the sample space is 50. So the probability that a white golf ball is drawn from the bag is equal to 20 divided by 50, or 2 over 5. The complement of an event. Given an event A, its complement is not A. It is the event when the event is not A. It is denoted by this symbol, not A. Other books use this notation for the complement of an event. For example, a bag contains golf balls. So this is our earlier sample space or earlier experiment. There are 50 of them, 20 are white, 10 are green, 15 are yellow, and 5 are orange. If B is the event a white golf ball is drawn from the bag, describe not B. So what is not B? Not B is the complement of event B. So not B is the event when the golf ball that is drawn is not a white golf ball. So this is our earlier experiment. Let B be the event a white golf ball is drawn from the bag, okay? And we know how to compute for P of B. It is equal to the number of instances when a white ball occurs in the sample space. So we have 20 white balls divided by the size of the sample space. It's 20 over 50, or it is equal to 2 over 5. Now, what is the probability that a ball that is drawn from the bag is not a white golf ball? So we will count the number of events, okay? In our sample space wherein the golf ball is not white. And there are 30 of them, okay? 10 plus 15 plus 5, that is 30. And so, P of not B, the probability that the ball that is drawn is not a white ball is equal to this, 30 divided by 50, or 3 over 5. If the size of the sample space is capital N and the frequency of event E is small n, and capital N is equal to small n plus m, the probability of not E is equal to capital N minus n divided by n, or okay, you can decompose this into two fractions, n over n minus n over n. And what is n over n? N over n is just 1. And this one is the probability of E. Okay, this is the probability of E. Okay, so let us go to this. What is the probability that the card drawn from a deck of 52 cards is not a spade? Well, you know that there are 13 spades, 13 hearts, 13 diamonds, and 13 clovers. So you have something like 39 cards that are not spades. So if you were to use the frequency method, the probability that the card that is drawn is not a spade is equal to 39 over 52. But we can also use it using the probability that the card that is drawn is a spade, using this. The probability that the card that is drawn is not a spade is equal to 1 minus the probability that the card that is drawn is a spade. And it is equal to 39 over 52, the same probability. And 39 over 52 is equal to 3/4. Two events A and B are independent if the probability of one stays the same whether the other event happens or not. And what could those be? What are some examples of independent events? Winning a lotto jackpot and passing a course in math. The baby born is a boy, and the die, I'm referring here to the experiment of throwing a die or rolling a die. So the baby born is a boy, and the number that shows after rolling a die is number 6. The card that is drawn is an ace of spades, and the number that appears in one roll of a die is 1. So I'm saying that these are examples of independent events because we cannot see how the probability of one event will affect the probability of the other. So it's like there is no connection here, okay? And so when people say everything is connected, well, I don't think so. I do not agree with that. There are things that are not connected at all. Nothing connects them. And these are examples of independent events. So random thoughts about independent events are the following independent events. Okay, the numbers drawn in a wetang. Okay, you're familiar with wetang. And the number you saw from the plate number of a car. Sometimes I see people who are into wetang, they are into this kind of a superstition. Okay, so let's say, for example, there was an accident, they saw the plate numbers of the car, and you know what? Some people who play wetang will bet on those numbers. Okay, because they see, okay, in their mind, they see that there is some connection between these two events. A catastrophe you saw in a dream, okay, I'm talking here about the dreams, the lucid dreams that you see when you are asleep. A catastrophe you saw in a dream and an accident that happened to you the next day. Are these independent events? The road that you saw in a dream. Again, I'm talking here about dreams. The lucid and vivid images we see when we are sleeping. You saw a road in a dream. And the next day you began an important project. Maybe your capstone project. Are these things independent events? You know what? When I said earlier that it's not true that all things are connected, yeah, that is not true. But there are really cases wherein things which many imagine to be not connected are in fact connected in some ways. Okay? Okay, so how do we compute for the probability of independent events? If events A and B are independent, the probability that both A and B will occur is given by this. P of A and B, the probability A and B will both occur is equal to P of A times P of B. The probability of event A times the probability of event B. So let's say, for example, A is the event when a spade is drawn from a deck of 52 cards. B is an odd number. B is the event when the number that appears in a roll of a die is an odd number. So let us compute for P and B. How do you compute for A and B? Or how do you interpret A and B? Okay, so you have an experiment. You pick a card and then you throw a die. What is the probability that the card that will appear is a spade and the number that will appear is an odd number? Okay, so it's P of A times P of B. P of A is equal to 1/4 because 1/4 of a deck of 52 cards is all spades times, okay, so the odd numbers in your die are 1, 3, and 5. So it's 3/6 or 1/2. So the probability that A and B will occur is equal to 1/4 times 1/2, which is equal to 1/8. Dependent events. Two events A and B are dependent when the probability of one occurring is affected by the occurrence of the other. Example: studying for an exam and passing an exam. So the probability of you passing an exam depends on the event of you studying or not studying for that exam, preparing for an interview and passing an interview, dying from COVID-19 infection and existence of comorbidities. If you have some health issues, hypertension, diabetes, heart disease, your probability of dying from COVID-19 infection is different if you didn't have those comorbidities. Hypertension and exercise, hypertension and diet. So these are examples of dependent events. Okay, so how do you compute for the probability of dependent events? If A and B are dependent events, then the probability that A and B will happen is equal to the probability of A times the probability of B given that A happened. So this is not just simple multiplication. When they are independent, it's just P of A times P of B. But not so with dependent events. It's P of A times P of B given that A already happened. So this is our example. An urn contains 5 white marbles, 3 green marbles, 2 blue marbles. 2 marbles are drawn one after the other without replacement. What is the probability the marbles drawn are green and blue? So A is our green marble. That is the event when green marble is drawn. And B is the event when a blue marble is drawn. What is P of A and B? P of A, the probability of getting a green marble from an urn that contains 10 marbles is 3 over 10 because we have 3 pieces of green marbles and the size of our sample space is 10. Okay, so this is an experiment wherein we are drawing one marble without replacement, one after another, okay? So this is like the first stage of your experiment. Okay, so when we now go to the second stage of our experiment, the probability that a blue marble will be drawn is equal to this, 2 over 9. Why 2? Because we have 2 marbles that are blue in our urn. But why 9? Because this is the second stage of your experiment. The quantity of marbles had been reduced. Okay? You already chose 1 marble from those 10 marbles. And so in the second experiment, you only have 9 marbles. Okay? So using your probability to compute for dependent events, the probability that A and B will happen is equal to this, P of A. The probability that a green marble is drawn, that is equal to 3 over 10 times 2 over 9. And so it's equal to this, 3 over 10 times 2 over 9. Okay, we cancel common factors. 3 over 9 is 1/3. 2 over 10 is 1/5. And so 1/3 times 1/5 is 1 over 15. That is the probability that the marble that you will draw from this urn, one after the other without replacement, is equal to this, 1 over 15.